Solubility is really dependent on a variety of factors. We are going to take a look at solutions and what affects their solubility. So if two solutions were mixed in a test tube and it results in forming a solid, how would that be classified? Something that would actually look like this. And what happened here is two aqueous solutions, which are transparent, were actually combined and formed a yellow mustard-like looking precipitate known as lead iodide. Now, why does this happen? Why do certain solutions, when mixed, form a solid? Looking at a reference table, table F. And table F is going to let you know in aqueous solutions, when certain salts combine together, what exactly the rules are for soluble formation of products versus what the rules are for an insoluble formation of products. When you get to AP chemistry, that's going to help you look at KSP, which is the solubility factor and constant for solutions. So what we're going to take a look at today is table F. Now table F has ions that form soluble compounds all here on the left hand side right there. And what that really means is that these ions are going to form soluble compounds with everything and anything, except when you look at the exceptions, when they combine with something. So when they combine with something, that's when we take a look at the exceptions to the rule. So for example, group 1 ions are soluble with everything. There are no exceptions. Ammonium, nitrate, acetate, and hydrogen carbonate, all of these don't have any exceptions. So that means they are soluble compounds with every single thing. However, now when we take a look at, let's say the halides, for example, chloride is soluble with everything except when combined with silver. Same thing for bromine and iodine. Lead combined with a halide is an exception. Mercury combined with a halide is an exception, meaning that when this combines with this, we form something that is known as an insoluble product. Insoluble means it is a solid that forms in a result of mixing those ions in a solution. And what that solid is called is a precipitate. A precipitate is a product that is insoluble. Okay? If we take a look at the right side of the chart, we look at ions that form insoluble compounds except, which means all of these, carbonate, chromate, phosphate, sulfide, and hydroxide, are insoluble with everything except when combined with these, and these. So, carbonate is insoluble with everything except when carbonate is combined with group 1 ions or ammonium, it becomes soluble. Hydroxide, all the way at the bottom, is insoluble with everything except when hydroxide is combined with group 1 ions, calcium, barium, strontium, or ammonium. If you form ammonium hydroxide or calcium hydroxide or barium hydroxide or strontium hydroxide, that means that you will have formed soluble. So when these combine with the exceptions, it forms a soluble product, which means an aqueous solution. So all that comes down to is, how can we tell whether silver chloride is soluble or not? How can we tell whether magnesium hydroxide is soluble or not? And so what we're going to do is look at table F and decide, following the solubility guidelines, if these are indeed soluble or not. And so using table F, we can look at, for example, silver chloride. So chloride is a halide, and silver is an exception. An exception to being soluble is insoluble. So that means that silver chloride would be insoluble. A precipitate would be formed in that solution. Versus now magnesium hydroxide, if we take a look at magnesium hydroxide, what you're actually going to see is we go to hydroxide and we look at hydroxide, and you see that group 1, calcium, barium, strontium, magnesium is not on the list because magnesium is group 2, not group 1. So that means it's insoluble with everything unless it's in the exceptions, and it's not in the exceptions. Thus, as a result, magnesium hydroxide is as well insoluble. Now the next thing we're going to take a look at is calcium hydroxide. And so calcium hydroxide, we go back to the hydroxides. And what we see when we go back is that calcium is an exception. See, it's right there. And what happens is calcium, being an exception to insoluble, makes it now soluble. Okay. Now if we look at nickel sulfate, for example, sulfates are down here on the left corner of the table F. Nickel is not in the exceptions. And because nickel is not in the exceptions, we don't have to worry about it now. And that means that it is soluble with everything. And since nickel's not an exception, that makes it soluble as a sulfate combination. Next, we take a look at magnesium sulphide. Well, ladies and gentlemen, the sulphide is right here on the right-hand side of your chart. Only exception is group 1 or ammonium, and that would be exception to insoluble, which would make it soluble. And now what we do is we're going to take a look and see what's combining with magnesium. Magnesium is not in group 1, nor is it ammonium, so because it is not an exception, that indeed makes it insoluble. Next is calcium carbonate. So we go to the carbonate group, not hydrogen carbonate. You have to go to carbonates. Carbonates are right here on the right-hand side. Calcium is not group 1 and it is not ammonium. Therefore, it is not an exception, so it makes it insoluble. Then we take a look at potassium hydroxide. Hydroxide is all the way at the bottom here. Hydroxide's only exception is group 1, calcium, barium, strontium, or ammonium. So if we take a look at the question, it is potassium. Potassium is indeed a group 1 metal, making it an exception to this rule. Thus, it has to be soluble. And then last but not least, ammonium nitrate. Nitrates, as you'll note to self, are on the left-hand side of table F. There are no exceptions, making it soluble with anything it comes into contact with, and thus as a result would be soluble. Okay, now these are the same process. So which is insoluble, meaning which of these is going to actually form a precipitate. So we're going to take a look at that right about now. All right, we've got a mess with the ink here, but we're going to deal with it. So potassium carbonate or zinc carbonate. So let's take a look. Exception is group 1 with carbonate. And so since group 1 is an exception to carbonate, that means potassium would be soluble. So we're looking for what is insoluble, which then leaves us with zinc carbonate as our answer. Next is which is soluble, potassium sulfate or barium sulfate. So let's take a look at sulfates. The exception to solubility would be with barium. So barium sulfate would be insoluble. We're looking for what is soluble, which means the previous one, potassium sulfate. Solubility rules in simple layman's terms is like dissolves like. So what does that mean? In terms of molecular polarity, we're talking about polar solutes will dissolve in polar solvents. And nonpolar solutes will dissolve in nonpolar solvents because like dissolves like. This is the reason why certain laundry detergents and soaps can take out grass stains, blood stains. And the thing is sometimes you'll wash clothes and you'll notice certain stains don't come out because you're not using soaps that have the same polarity as the substance that has stained your clothing. Which is why when you wash your hands, you don't only wash your hands with water, you wash your hands with soap. Because the soap can dissolve all the grimy, basic substances off your hands, where the water can then rinse it down the drain. Using your knowledge of like dissolves like, you're going to determine if the following compounds will dissolve in each other, and explain your reasoning for having made this determination. NH3 is a polar molecule. H2O is a polar molecule. Polar meaning it has only one line of symmetry, making it have an asymmetrical distribution of charge. Because of that, it has poles in the molecule. Therefore, a polar solute can dissolve in a polar solvent, and yes, it is soluble. Why? Because polar solutes can dissolve in polar solvents. Now, if we take a look at methane, methane is nonpolar because it has asymmetrical distribution of charge, meaning there is symmetry of the electron density around the entire molecule. Whereas water is polar because it has an asymmetrical distribution of charge, making it an uneven distribution of charge around the molecule. So, are they soluble? No, indeed they are not. It's like trying to dissolve oil in water. It just will not work. Okay? Why? Because only like polarities can dissolve in one another. Iodine is extremely nonpolar. It's a diatomic molecule, which means it does have a symmetrical distribution of charge. Because the charge distribution is symmetrical around the entire molecule, it will not be able to dissolve in a very polar substance like water. Therefore, no, for the same reasons as above. Now, iodine, nonpolar, in addition to methane being nonpolar, they have extremely symmetrical distribution of charge around the entire molecule, making their polarities the same, and therefore it makes them soluble in one another. Ammonia, very polar. Methane, very nonpolar. Because of this, they do not have the same molecular polarity, therefore they cannot dissolve in one another. So you may be wondering why precipitating these tables were beyond the solubility rules. You learned last semester about double replacement reactions. And a double replacement reaction means that a reaction has gone to completion. And what that means is it's not reversible. It can't be changed. Nothing can be changed about it. The reaction is finished, and nothing will ever change about it. So, 3 signs that a reaction has gone to completion are formation of water in your product, formation of a gas in your product, or formation of a precipitate. You only need one of the 3 signs in your products to know that the reaction has gone to completion. So let's take a look. HCl plus NaOH, if you were to do a double replacement reaction, H would be switching places with Na. And what that would do is create HOH, which is also known as water, and NaCl, a salt. And so what happened is H switches places with Na at the back end, where Cl will now combine with Na, and OH will combine with H. HOH, simply put, is a water molecule, HOH, and so also known as H2O more commonly in a formula. And what this type of reaction represents is something you're going to learn later on, which is HCl, which is a strong acid, reacts with a pretty strong base, sodium hydroxide base, and you form water and a salt. Now, the reason why this is a sign of a double replacement reaction, or something that has gone to completion, is because water is in our products. When taking a reagent, the only way you're going to know that your double replacement reaction formed a gas is in your products. You'll see X and Y, let's say, plus B and Z goes to X, Z plus B, Y, and one of them will be in a gas phase, one of them, let's say, is a liquid phase. So the second you notice that you've had a double switch and you have a gas formed in your products, that's another sign that a double replacement reaction has occurred, because your products will take themselves out in either the gas form or in terms of becoming a solid. So an example of the formation of a solid would be when you form a precipitate, where you go to table F and you note that a precipitate was formed. So for example, let's say we reacted HCl with AgNO3, and we reacted it, and our products would be a double replacement reaction, where now H is going to switch places with Ag, so H becomes NO3, and Ag will now combine with Cl. And if you look at table F, you'll note that silver with chloride, the exception to chlorides is silver, and it is an exception to being soluble, so that makes it a solid. Solid product is the precipitate. Or if you're taking a reagent exam and you notice that you see a solid in a double switched out reaction, then the formation of a solid automatically tells you that it is a double replacement reaction and it has indeed gone to completion.